Welcome to my lab number 5. So as an introduction, lab 5 focused on a mini capstone projects, and I chose to analyze the motion of a falling slinky using the video on Canvas. This experiment sought to observe the motion of a falling slinky and to compare a computational model to that observation. A position versus time graph was created using tracker analysis, and then another one was created using GlowScript. The goal of this experiment was to predict the motion of a falling slinky through the prediction of the effect of gravity and drag. My main findings include that the computational model was accurately depicting the observation of the motion of the slinky. And my system equals the spring and the surroundings equal the Earth. Some key physical concepts that we should know is Newton's second law, which states that the change in momentum over the change in time is the net force, and that can be rewritten into the velocity update formula and the position update formula. Other equations that we need to know is the weight force, force tension, and the drag force, and these are all things I'll talk about later in the video. So using Tracker as an observational model, so as you can see, what we're really interested in is the bottom of this slinky or spring, basically. So when he first holds it's held up here and then stretched down due to gravity. But when he lets go, the bottom actually doesn't move for a specific amount of time, as the top is basically catching up to the bottom. So I recorded using Auto Tracker the movement of the bottom of the spring, and this is what I got. So these are all my data points, and these are the graphs. Basically, what I did here is I calibrated this using the height of the man as about 1.8 meters. And then I found the given mass of the slinky online, which is 0.204 kilograms. The initial position, the initial velocity is just 0, and then the final position, that was given off my data table. And then some disclaimers is that a data point was taken every 0.033 seconds, and a data point was taken at every single frame. Basically, all that we're interested in here is the movement in the y direction, since it's really just one-dimensional. So as you can see, the bottom of the spring doesn't move, and then once the top of the spring reaches the bottom of the spring, then it descends towards the ground. So coming up with a computational model, it's important to include these initial conditions, including the ball mass, initial position, my delta t, my gravity, or my j hats just in the y direction, like I said. And then for my drag constant, I actually just did trial and error to get 35.243. And basically I found that the last value was closest to my observed last value. So for a computational model, so I split it up between the code before the top reaches the bottom. So that was less than 6.033 seconds. So in doing that, I have my weight force, and then the tension force is negative due to gravity for this time. And we also have our velocity update formula and our position update formula. And then after, so while t is less than 8.833 seconds, we just have the weight force and the drag force, and then the net force is the sum of those. And we also have our velocity update formula and our position update formula. Okay, so these are the results of my computational model. As you can see, they're similar to the y position on tracker analysis. So it stays constant and then it drops. So I inserted both of the data points for my computational model and my observed model to create a graph through Google Sheets. And I have my computational versus observed. And basically, my conclusion is that the computational model was arguably very accurate, and then the slight difference can be accounted for through experimental error. These errors can include auto tracker inaccuracies through tracker analysis, inaccurate drag force estimation, since I really just did trial and error, and inaccurate calibration. So basically, the height of the man may not have been 1.8 meters. And then what if the drag force was unaccounted for? So if the computational model did not include the drag force, the model would be very inaccurate, since the spring would accelerate to the ground too fast in comparison to the tracker data observed. And then finally, what does it mean? So why does the bottom of the slinky not initially move? You may notice in the graph that the code was divided, and this is because the bottom of the slinky does not initially move. This is because the tension force pointing up is equal to the force of gravity, so therefore the spring compresses towards the bottom.